Hello again and welcome. Recently Dave Jones produced a video how to discharge capacitors safely using a multimeter. During that video he's using a television set as a prop, and what he's doing is he's showing the bulk capacitors, which are charged up to about 400 volts when the TV is on, and then he's placing the multimeter into its resistance mode and then attaching the leads across the capacitor to discharge it. Of course, I've done a fair number of transient tests with various multimeters using this homemade transient generator. This is putting out an exponential decaying pulse, and that's independent if you have a load attached to the output of this or not. Now, I have had some people write me before who claimed I was attaching the meters directly across the capacitor bank. Again, that's just ignorance on their part. The standards that I use to base this transient generator off of, those are available in the public domain. Again, this transient generator doesn't follow those standards per se. It's tweaked a little bit for what I was trying to achieve with my testing. So a couple of things during Dave's video caught my interest. One of the things he pointed out is that not all meters are the same. Some meters may not survive in that particular application. But the other thing I took away from that video is he's addressing people that are working from home. Maybe they're not a professional, and he's trying to give them a pointer on how they could discharge this capacitor bank. The first thing that comes to my mind was the microwave oven. Now, it just so happens, like last summer, our microwave oven went on the blink, and I had to do some repair work on it. One of the things that happened was the fuse blew, but I ended up having to rebuild the controller board to get that thing functioning again. We went to buy the fuses for that oven from the local repair shop, and they told my wife they wouldn't sell her the fuse. It sounds like they don't want to be liable for people getting injured while working on their microwave ovens. And that's a problem, because if you look out on the internet and do a search for fatalities, deaths from people trying to work on their own microwave is actually quite common. Typically inside of a microwave oven you have a 2000 volt transformer. That voltage is rectified and it's placed across a 1 microfarad capacitor. Calculating the energy of that capacitor, it's 1/2 CV squared, so 2000 volts at 1 microfarad gives us 2 joules. Now again, our transient generator here can put out about 20 joules, but I have a lot of safety features built into these transient generators to try to protect me from any kind of injury or death. Now, the guy at the local store refused to sell my wife the fuse for our microwave oven until she explained that, her husband had these sticks, and this is one of them here, that he was sticking inside of the oven, probing around to short that capacitor out. So what's inside of these is there's a set of series high voltage resistors, and then there's a voltage divider network to light up this LED, and I think this turns off once the voltage across this gets below about 10 volts. You can see the other side of the resistor bank comes to this wire here. So this is my discharge path, and of course I'm holding behind that even further. Once my wife kind of explained what I was doing, he ended up selling her the fuse, so I was able to get the proper fuse to repair our microwave. But what I'm interested in this video is, would a typical multimeter have a problem discharging a microwave oven capacitor using the technique that Dave shows in that video? I'm not sure. I'm not going to bring my microwave oven up here to run these tests. Instead, I've made this microwave oven simulator. So this is what it looks like. This happens to be the power supply out of one of those electric fly swatters. This will put out about 2000 volts. It is rectified on the output. You can see it's been modified slightly over the years. Up here I have a typical diode that you'd see inside of a microwave oven. And then I have this capacitor bank. I also have some bleed resistors here, and I have a voltage divider network here. This allows me to monitor the voltage across the capacitor bank. So these leads here will go off to a meter that we'll use to monitor that voltage. This is the power feed for our little DC to DC converter. There's one lead coming off of the ground side of this capacitor bank. This will go directly to the meter that we want to test. And then to test the high side, I don't want to be testing with the leads that come with the meters, because some of those are a bit sketchy. So this is nothing more than some high voltage test lead soldered up to this piece of copper wire, going through some rubber insulated tubing. So what we'll do is we'll just plug these two leads into the multimeter we want to test. We'll charge up this capacitor bank, and then we'll touch this lead to the top side of the capacitor bank. This capacitor bank is made up of 6 film type capacitors. You can see these are 1.5 microfarads each, and they're rated for 850 volts. Of course, 2 of these in parallel give us 3 microfarad, and then the 3 banks in series gives us our 1 microfarad. Again, I've got a 20 mega ohm resistor that's in parallel with each one of these. That's this guy here. And that's just to discharge this bank when I'm done with it. The other thing that I have is this divider network, and that's this resistor here, and this provides us a 1000 to 1 ratio. So if I'm reading 2 volts with the multimeter here, this bank has 2000 volts across it. Again, with these capacitors rated for 850 volts each, we can easily run this bank at 2000 volts. So again, in Dave's video, he shows using the resistance mode. Now, there's nothing really unique about that particular mode other than it's switching in this low voltage clamp that he's talking about. But again, that clamp is going to be engaged if the meter's in the millivolt modes, if it's in temperature, capacitance, diode check mode, continuity mode. All those will engage this high-speed, low-voltage clamp that he's talking about. The problem that I find with these different multimeters, and he kind of hinted to that in the video, while in the higher-end multimeters, I typically see a PTC, and it's always in series with a surge-rated resistor. On the cheaper meters, we don't always have this surge-rated resistor. The other thing I find that's different is the PTC that's used in a lot of the cheaper meters is only a 5mm diameter. So those PTCs are only rated for, I think, like 500 volts before they break down. And during my testing, I've shown many times where what's happened is it'll arc across the PTC and it'll blow the casing off of the PTC. Of course, once that arcs over, nothing's limiting the current anymore. That passes right on through to the rest of the meter. It destroys the multimeter. The whole idea of having this surge-rated resistor is we have another thing that's limiting the current while this thing is heating up. Again, when I'm hitting these meters with a transient like this, the transients typically have a full width half height of 50 microseconds. The thermal time coefficient of these PTCs is going to be very slow compared to this transient. So these just don't have enough time to respond and open up. So you're basically looking at a 1.3 k ohm resistor here. A lot of the meters I look at, they'll use a 1 k ohm series resistor. It's the combination of these two that's limiting the current through this clamp circuit. So here I have one of the free multimeters from Harbor Freight. I believe that this one I've already destroyed. Yeah. Let's go ahead and we'll just pop the cover on this real quick. You can see there is no surge-rated resistor, nor is there a PTC. They do have some resistors up here to try to limit the current in the different modes, but these resistors are not anything special. And what ends up happening with these cheap meters is they do break down, so they're not very robust. So you probably don't want to use a multimeter like this to discharge these capacitor banks that we're talking about. And the leads that are supplied with these are also very poor quality. Again, this is just not a combination that you want to use if you're working with line voltage rated appliances. This is one of the Uni-T meters that I looked at recently. This is a UT125C. This meter was damaged, but I have repaired it. I don't believe I put any batteries back in it the last time I used it. Yep, no batteries, but I'm sure it works. So let's go ahead and we'll take this meter apart real quick. Notice here are our 2 PTCs, and then we have 3 MOVs. The way that this meter works is the input probably goes to the 2 different PTCs, and then these 2 PTCs go to these 2 MOVs. These are tied to this common point here at the center, which goes to this MOV back to our return path. But you'll notice that there is no surge-rated resistor in series with either of these PTCs. Now, part of the problem with testing this particular meter, you can see the leads are permanently attached to it. So what we're going to be doing is pulling off these little sheaths, like so. And we just have some adapters. We'll attach these to our leads, like so. And then we can go ahead and plug this into our little transient generator, like so. And we can attach our test lead like so. Again, there's basically nothing across this bank right now, so we should be able to read this 1 microfarad. Let's just see. There you have it. So 0.993 microfarads is what it's showing. Let's just try reading that with our little Uni-T meter. So again, we'll go to capacitance mode. Here you go. It's 1.014 microfarad. This is probably pretty close to what you're going to see in a typical microwave oven. So here I have my 2 Bryman BM869S's. This one is attached to the output of this divider network. The other one will attach right across the capacitor bank, like so. Now these 2 meters should basically track. What I'm going to do now is go ahead and turn on our power supply. You can see the 2 are tracking fairly well. So this is 10 millivolts, which is roughly 10 volts on this meter. 200, 250, 60. What I'm going to do now is just go ahead and disconnect it, and you can see with our 20 mega ohm resistors, this will discharge this bank fairly quickly. So there's 1,000. What I'm going to do now is just go ahead and disconnect our Bryman on the right, and we'll just continue to track with this other meter. So there's 18, 19, and there's 2,000 volts. Now what we're going to do is take our little Uni-T meter, which again is placed in the resistance mode, and I'm going to attach this directly across this capacitor bank. So let's see what happens. Well, it should discharge pretty quick. Now what I'm going to do is try shorting the 2 probes together, and let's see if we damaged it. You can see it's still reading 0 ohms. Here it is with an open. Let's just try it again. Again, here's 2,000 volts. And it looks like no damage. Pretty interesting. I'll go ahead and turn off our little power supply. Again, the bank is discharged. Now what we can do is a little quick functional test on our little Uni-T meter. Right, this should be roughly 50 ohms. And you can see it's reading 50.2. This would be 1 k ohm. And you can see it's reading 1.000 on the spot. This is a 10 k ohm 1%, and it's reading 10.02. Here's 100k. It's reading 100.1. Here's a 1 meg. It's reading 1.001. And here's a 10 mega ohm. And you can see it's reading 10.01 mega ohms. Can try it real quick in diode check. See, that's working fine. And here it is in the continuity mode. Of course, that still works fine. So yeah, we probably have not damaged this meter at all with this testing. Now again, because this meter was damaged, I did not use the same transistors for the high-speed clamp with what originally came with it. So would this meter survive this testing had I not put different transistors in there? We really can't be too sure. So would I suggest using this UT125C to discharge your microwave capacitors? Just from a safety aspect, I wouldn't do it. Again, there's just safer ways to discharge the capacitor banks. So here we have the Kiwis KM401. This is a meter that I had previously looked at as well. And again, this meter was also damaged. So the high-speed clamps on this have been replaced. Again, I probably did not use the OEM's transistor. so this meter may not behave the way it did originally. Now this particular meter, again, has no surge rated resistors, and it has the smaller bodied PTCs. But again, the clamp has been changed on this meter. Let's go ahead and we'll install a battery. All right, we'll just be using 3 envelopes. Looks like it powers up just fine. And let's go ahead and just attach our 2 leads. All right, let's turn on our power supply. It's about 1500. There's roughly 2000 volts there. Now let's see what happens. Looks like a discharge fairly quickly. Let's see if it'll still read resistance. Looks like it does. Oh, look at this though. It's reading 3K ohms. All right, let's turn off our power supply. Remove our leads. Ah, you can see that. So it looks like it's leaking now. Let's have a look. Yep, you can see it's stuck on 3K. So those transistors that I'd replaced before, whatever I used, they weren't beefy enough to handle this transient. Let's just try this in capacitance mode real quick. Does it zero out? And let's just see if we can read anything. Oh, you can see it's reading 1.012 microfarad. There you go. 1.013. So the capacitance is working fine. Let's try the diode check mode. That seems to be working. Yeah, it's just the resistance mode that seems to be out on it now. The problem is I don't have a lot of low-end meters left. Typically those meters are damaged beyond repair. They may end up getting stripped for a few parts here and there, but the rest of it just basically goes into the recycle bins. I do have a few other low-end meters that I'd like to evaluate. There's this Astro AI, and there's this Electricity. Again, these are still brand new in the box, waiting for me to eventually pull them out and run them through the full-on transient test. So maybe we'll include this little microwave oven simulator as part of that testing. Now again, if you're servicing a microwave, I would not recommend that you try to discharge those capacitors with a meter like what Dave's showing. That's just me. Of course, you're free to do whatever you like. Well, I think that's going to be it for this video. I doubt I'll be making another one before the end of the year, so hope you enjoy your holidays, whatever it is that you celebrate. And maybe we'll see you in the next video next year. Till then, later on. Here's with 50 ohms, 100, 1K, 10K, 100K, 1 meg. Let's try 10 meg. Let's try it in capacitance mode. And this will be a 1 nanofarad. Say 0.1 microfarads, 150 picofarads, and a 1 microfarad, 10 microfarads, and a 100 microfarad. And we'll just switch it to temperature real quick. This should be roughly 500 degrees Celsius. Good enough. And this is diode check mode. Here's with a short. Here's a single silicon diode. Here are 2 in series. This should be roughly 5 volts DC. And let's try it in the AC mode. And this should be 2.5 volts. And let's try it in frequency. Again, this should be 60 hertz. Looks fine. I'll go ahead and tuck it back away for later.